Ever wondered what makes a blade truly sharp? I'm not just talking about your kitchen knife that can barely slice a tomato. I mean razor sharp, a level of sharpness that feels almost magical. Today, we're embarking on a journey through time and technology to uncover the secrets behind the perfect edge. From the first sharpened stones of our ancestors to the mind-boggling precision of modern factories, we'll explore how humanity has chased the ultimate cut. It's a story of innovation, physics, and a relentless quest for perfection. So, grab a seat, and let's dive deep into the world of blades. Let's rewind the clock. Way back, picture our earliest ancestors. Their survival depended on tools, and the sharper the tool, the better their chances. The very first blades weren't metal, they were stone. Flint, obsidian, chert, these were the materials of choice. By striking one stone against another in a process called knapping, they could flake off pieces to create an edge. This wasn't just random smashing. It was a highly skilled craft. An obsidian blade, when knapped correctly, can have an edge that is phenomenally sharp, even rivaling modern surgical scalpels at a microscopic level. Imagine the patience and knowledge required to read the stone, to know exactly where and how hard to strike to achieve that life-sustaining edge. This was humanity's first foray into the art of sharpening, a fundamental skill that literally shaped our destiny. From these humble stone beginnings, the discovery of metals changed everything. First bronze, then iron, and finally, steel. Each new material presented new challenges and new opportunities for creating a better, more durable edge. Early metal blades were often soft and would dull quickly. The real breakthrough came with the understanding of heat treatment. Blacksmiths became the new masters of the edge. They learned that by heating steel to a specific temperature and then cooling it rapidly, a process called quenching, they could make it incredibly hard. But hardness alone isn't enough. A blade that's too hard can be brittle and snap. So they developed tempering, a process of reheating the hardened steel to a lower temperature to reduce brittleness and add toughness. It was, and still is, a delicate dance of fire and force. The sound of the hammer on the anvil wasn't just noise, it was the sound of science in action, forging the very structure of the metal to create an edge that could hold its sharpness through battle or a long day's work. This ancient art of the blacksmith has evolved, but the core principles remain the same even in today's most advanced factories. Let's step inside a modern knife manufacturing plant. It's a symphony of high-tech machinery and meticulous quality control. The journey begins with a sheet of high-carbon stainless steel. This isn't just any steel. It's a specific alloy, carefully formulated for a perfect balance of hardness, toughness, and corrosion resistance. Lasers or hypersure water jets cut out the basic shape of the blade, a process called blanking. These rough shapes, or blanks, have no edge at all. They are the blank canvas for what's to come. The precision here is incredible, ensuring every single blade starts with the exact same dimensions, a crucial first step for consistency. It's a far cry from a blacksmith eyeing a piece of glowing metal, but the goal is identical, to create the perfect foundation for a sharp blade. After the blades are cut, they move on to the most critical stage, heat treatment. Just like the blacksmiths of old, modern manufacturers use heat to transform the steel's molecular structure. But instead of a charcoal forge, they use massive computer-controlled ovens. The blades are heated to a precise temperature, often over 1000 degrees Celsius. Held there for a specific time to ensure the carbon is evenly distributed, and then rapidly cooled, or quenched. Some methods involve quenching in oil, while others use a blast of supercooled nitrogen gas in what's called a cryogenic quench. This process, known as hardening, rearranges the steel's crystalline structure into a form called martensite, which is extremely hard but also brittle. This is where modern science truly shines. The level of control is absolute. Computers monitor every variable to ensure each blade achieves the maximum possible hardness for its specific steel type. A hardened blade is like a piece of glass, incredibly hard, but it will shatter if you drop it. To make it a useful tool, it needs to gain some toughness. This is achieved through tempering. The hardened blades are placed back into another set of ovens, this time at a much lower temperature, typically around 200 degrees Celsius. This carefully controlled reheating process relieves the internal stresses created during quenching and slightly softens the steel, making it less brittle and more durable. The final balance between hardness and toughness is determined by the exact temperature and duration of the tempering process. Different knives require different balances. A flexible filleting knife needs more toughness, while a chef's knife might prioritize edge retention, which comes from hardness. It's this precise manipulation of material properties that defines a high-quality blade. Now, with the steel perfectly treated, it's time to create the edge. This is where the grinding happens. The untempered, edgeless blade blank is taken to a series of grinding machines. These aren't your grandpa's bench grinders. We're talking about robotic arms and CNC machines fitted with abrasive belts of varying grits. The process starts with a coarse grit to rapidly remove material and establish the primary bevel, the main angle of the blade's edge. Then, the blade moves through progressively finer grits. Each stage refines the edge, removing the deeper scratches left by the previous belt and creating a smoother, more uniform surface. The angle at which the blade is ground is absolutely critical. A smaller, more acute angle will result in a sharper but more delicate edge. A larger, more obtuse angle creates a stronger but less sharp edge. For most kitchen knives, this angle is typically between 15 and 20 degrees per side. The goal of this stage is to create a clean, consistent V-shape along the entire length of the blade. After the primary grinding, the blade is sharp, but it's not razor sharp yet. If you were to look at the edge under a microscope, you'd see it's still quite rough, covered in tiny parallel scratches from the grinding belts. The final step to achieving that scary sharp finish is honing and stropping. Honing realigns the very tip of the edge. In factories, this is often done on specialized wheels made of hard felt or other materials. But the ultimate refinement comes from stropping. A strop is typically a strip of leather, often coated with a very fine abrasive compound, similar to a jeweler's rouge. The blade is gently pulled across the strop, with the edge trailing. This action polishes the microscopic teeth along the edge, removing any remaining burra, tiny, flexible wire of metal that clings to the edge after grinding and refining the apex of the edge to a mirror-like finish. It's this final polishing step that takes a blade from merely sharp to exquisitely sharp, capable of gliding through paper with no effort at all. So, we've seen how a blade is made, but what is sharpness on a scientific level? At its core, sharpness is about concentrating force. A sharp edge is an incredibly thin point. When you press a sharp knife against something, all the force you apply is concentrated onto that tiny, almost non-existent surface area. The pressure becomes immense, high enough to sever the molecular bonds of the material you're cutting. The thinner the edge, the less force is required. That's why a sharp knife feels like it cuts effortlessly. The science behind it is all about geometry and material science. The blade's overall geometry, or grind, affects how it moves through material after the initial cut. The microscopic geometry of the very edge determines the initial sharpness, and the steel's metallurgy determines how long that microscopic geometry can be maintained before it deforms or wears away. A quality we call edge retention. It's a beautiful interplay of macro and micro engineering. From the first chipped stone to the laser-cut cryogenically quenched supersteel of today, the quest for the perfect edge has been a constant driver of human ingenuity. It's a journey that combines ancient artistry with cutting-edge science. The blacksmith's intuitive feel for the heat of the steel and the modern engineer's precise control over molecular structures are two sides of the same coin, both striving to create a tool that is as efficient and as perfect as possible. The next time you pick up a quality knife, take a moment to appreciate the incredible journey it represents. The balance in your hand, the glint of light off the polished edges, the culmination of thousands of years of trial, error, and relentless innovation. It's more than just a tool. It's a piece of history, a work of science, and a testament to our enduring desire to shape the world around us. Thank you so much for joining me on this deep dive into the art and science of sharpness. If you found this fascinating, don't forget to hit that like button and subscribe to the channel for more explorations into the technology and history that shape our lives. Let me know in the comments what you'd like to see us uncover next. Stay sharp, and see you in the next video.